Okay, so perhaps you have taken a couple of minutes here. X is greater than or equal to 2. I mean, I guess theoretically, I mean, to do this right, I should be writing this notation. It's a set of all x, y, z such that x is greater than or equal to 2. This will put me exactly in the two-dimensional space, which, of course, is where I am, where I should be. And so that's the correct theoretical notation. And so what kind of points are we talking about? What kind of, basically the answer is some set of one subset of points in the three-dimensional space. And the way we look at this is, well, if x is going to be greater than or equal to 2, again, let's try to draw what I called a canvas. Okay, so this would be like a vertical wall that goes through the point x is equal to 2. Okay, so that's a set of points where x is all the way up. I mean, every point on this plane has the property that x is equal to 2, right? And in fact, every point where x is equal to 2 is on this plane, assuming that this plane goes infinite. Now, if x is to be greater than or equal to 2, I'm talking about this entire points, entire space, half space that's right in front of this plane, right? So it is kind of hard to draw this on a piece of paper or on a tablet screen, but hopefully this will make it clear that I'm talking about all the points on the plane and sort of in front of the plane where x is greater than or equal to 2. So it is hard to describe it. It's hard to even say it verbally, but of course that set theory notation or mathematical notation makes it much more precise, which points what we are talking about, right? So we will refer to this set as a half space. Why is it half and not 40% or 80%? Well, since we're talking about an infinite space, there is really no half, right? But one side of a plane is always considered a half plane or half space in mathematics. All right, the next one. Basically, I mean, this means that z is equal to y squared, right? And you may have noticed it is an equation of a parabola. X is missing. And so what does it mean when x is missing? Well, x is missing. That means that anything, whatever x we can come up with is okay, right? And the way to draw a picture when a variable is missing is something that you probably should be familiar with, right? So first I'm going to draw this three-dimensional space. Z is equal to y squared on the canvas where x is equal to 0, which is called the yz plane. If you were to graph this equation on yz plane, what you will get is this parabola. Okay, it's a standard parabola that goes up, and it goes through points like 0, 1, 1, 0, 2, 4, 0, 3, 9, and so on, right? And then because x is missing, what we do is we just kind of keep drawing this like that, right? Just extend it along or parallel to in the direction parallel to the x-axis. And so all of these points are considered to be a part of this. Okay, so you see what I'm talking about here? It looks like a trough, or like a sort of a gutter or something like that. And so this is sometimes called a parabolic cylinder. Okay, and we'll be discussing what to call these surfaces in the near future. But at this point, I want you to be familiar with how to visualize what is written in terms of equation involving x, y, and z. Okay, we will have a lot more to say about these things in section 6. So yeah, section 6. But at this point, it's sufficient to just see some of these examples. All right, now in R3, we have a distance formula. Now I have already referred to this when we talked about the norm of a three-dimensional vector. But if you have a point P And if you have a point Q, the P is xy, x1, y1, z1, and Q is x2, y2, z2, then the length of this vector, actually, you can just write that as PQ, okay? Because if you just write PQ without anything on top, it means that it's supposed to mean the distance between P and Q. But to be technical, because we are studying vectors, and this will be referred to as the vector from PQ, and the magnitude of that vector is, all right, so again, I have to have a long square root, okay? You just try to make them really long, okay? Then you don't have to keep extending them. All right, so this will be, and again, you probably are familiar with this, x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. Okay, and so it should look very familiar because all you are doing is really extending the Pythagorean theorem into the three-dimensional space. Okay, so I have the two here, right? And so, and again, you can visualize this sort of because you know, you have this. I mean, here's the length. What is this thing here? That is the hypothesis of that you know, triangle that's projected on xy plane. And the length of this is the square root of x squared plus y squared. And then, of course, you have the z that goes perpendicularly. And so using the Pythagorean theorem again, using this right triangle, okay, and the right angle is right here, okay, so you have the square of this number, which is x squared plus y squared, and the square of this number, adding together would be the square of the length of this hypotenuse, and that's what we're looking for, and that would be the square root of the sum of the squares of the difference between the individual x, y, or z coordinates. All right, so with that, we can talk about the definition of a sphere, right? As you know, the sphere is basically the surface of a ball, a perfect ball, if you can imagine that. And it is a set of all points, a sphere is a set of all points in R3 equidistant from a fixed point. And that fixed point, we typically, and we all, well, let's see. We almost always denote that fixed point as written here. It's x naught, y naught, z naught. That's the fixed point. This distance, which is fixed, and that is the distance by which every point on the sphere is separated from the fixed point, the center point. And this distance is radius r. Okay, and by the way, this fixed point is often called the center for an obvious reason. And so every time we talk about a sphere, we can talk about the center and the distance and the radius. And it turns out if you specify a radius and a fixed point, the center, then you can define the unique sphere. Right? Oh, by the way, sometimes this is called, and maybe it's a surprising thing, but this is among the mathematicians, okay? We call this a two-dimensional sphere. And you say, wait, how could it be two-dimensional? Because it's in three-dimensional space. Exactly, this is sitting in the three-dimensional space, but because we are not talking about everything inside, right? Do you notice that? The points outside the sphere are, of course, not the part of the sphere, but neither are the points inside. Okay, so all those, I mean, the sphere is this hollow thing. It's only the surface of the ball. Everything inside the ball is not part of the sphere or a point on the sphere, because remember, it has to be equidistant, right? Inside would have a distance less than r, and so we are just talking about the outside surface. And that surface is, by definition, of course, a two-dimensional thing locally. And so this is called a two-sphere, or S2 is what we name this. This is the precisely mathematical definition of what we are trying to say. Okay, well, so how do you describe this? The set of all points on the sphere, right? The equation of the sphere is simple, because what we are saying is if you pick any random point x, y, z on this sphere. Oh, by the way, and this is a great sort of analogy or metaphor to understand the relationship between equations and a geometric object. Let me put my face in here because I want to just talk to you here. Okay, so you know, everything from like equations of lines, equations of sphere, equations of circles, right? You know the relationship between equations and the geometric object defined by the equation. Okay, that didn't come until about 400 years ago when Descartes came up with how to use algebra to describe geometry. Okay, until that point, geometry and algebra were completely different things, and they studied them independently. Thanks to Rene Descartes, now we can describe geometry in terms of algebra. Okay, and so every time you are trying to come up with an equation of a geometric thing like a circle or a sphere, here's how you ask the question: what makes that point so special that it belongs to that sphere, for instance, in this case, all right? So I have this random point XYZ, right? What makes that point XYZ so special that it becomes the part of this thing called the sphere with a center point X naught, Y naught, Z naught, and with the radius R, okay? Said another way, it's like being a prestigious member of a exclusive club. You have this person called XYZ, and how does he or she become or belong to the exclusive member of this club called the sphere of radius R centered at X naught, Y naught, Z naught, okay? And it turns out there's only one criteria, one eligibility requirement for XYZ to be a member of this exclusive club called the sphere, right? All right, let me go back. So what is this, the equation that XYZ has to satisfy? The only thing is for this guy or person or point to be a member of this sphere. The only eligibility requirement is that its distance from the center point is R, okay? And so how do you write that using mathematics? Well, we have the formula, the distance formula, okay? So the distance formula calls for this requirement, because my computer is lagging in time, so, and I think I just wrote down some mistake. I can't fix it until I see it. All right. Oh, no, I didn't write a mistake. Okay. So it's the square root of this whole thing, right? So that's the distance between, it should be longer here. This is the distance between X, Y, Z and X naught, Y naught, Z naught. Okay. So imagine you are X, Y, Z. X is your first name, Y is your middle name, Z is your last name. And X naught, Y naught, Z naught is this fixed point. And you walk in, a man walks into the bar, XYZ walks into the bar, and says, hey, I would like to be a member of this sphere. And they'll ask you just one question. What is your first, middle, and last name? So they enter your X, Y, and Z as your first, middle, and last name, and they will put your name into this formula. If this number, the square root of this thing, comes out to be R, okay, then you are eligible. Welcome to the club. Otherwise, you can't be a member of this club unless you change your name or your position. All right, so that is the equation of the sphere, right? This describes every point on the sphere. But since we don't like to have square roots, often we just write this without the square roots. Very slow, and I don't like it, but this is coming up like very slowly. The equation of the sphere of radius R centered at X naught, Y naught, Z naught is what you are about to see here. This is equal to R squared. Now, you probably have seen this in some other algebra class, but I hope you understand why you use this equation. You know, don't just memorize the formula, which it's easy to forget. But if you understand this construction, of course, it's easier to retain this knowledge. And of course, it makes sense, right? Right, so that's the equation of the sphere. Now, if the sphere is written this way, that's a lot easier to understand. Let me just give you an example. I give you 3 examples and then pause the equation, take a little break here. Okay, right, describe or come up with an equation of the sphere with radius 4 and center 1, -2, 0. Okay, when you see the problem written here, you would see you can write down your answer, okay? And in fact, you can probably write your answer right now if you are able to do this. What is the equation of the sphere with radius 4 and center, oh, that doesn't look good, huh? 1, -2, 0. All right, so that should be a simple enough task for you. X minus 1 square plus, what is y minus -2, but of course y minus negative can be written as y plus 2 square plus, now of course it's z minus 0 quantity squared, but you don't have to write z minus 0 quantity squared. All you have to do is just write z squared. And if you stop here, of course, that's not even an equation, so I can give you full credit. Okay, when you write down the equation, when you're asked to write an equation, you really should have an equal sign. Right, and so this is this, oh, not 0. Did I just write down 0? Yeah. It's hard to write and talk at the same time. It should be the radius squared, right? So this will be the answer to that question. That's pretty easy, right? All right, so now I want you to work on this problem here. I'm going to write down some equation. First of all, I want you to think, okay, if you found a piece of paper on the street, a sidewalk, okay, and you're walking with your friends or maybe your family members, and you pick up a piece of paper, and this is all it says. All it says is x squared plus y squared plus z squared minus 6y plus 8z is equal to 0. Your friends will say, I don't know what that is. It's some sort of a code. Maybe it's it's a secret code that shows you something is going to come up or something. And your family will say, oh, I don't know what that is. And they will throw this away. And you look at it and you say, oh, no, that's a circle. No, that's a sphere. And they will look at you like, what part of this is round, right? Well, I mean, hopefully you know and recognize this as a sphere. And if you speak that language of mathematics, which other people may not understand, you'll say, oh yeah, of course, that's a sphere. All right, let's find the radius and the center of this, okay? Why don't you pause this for a moment and work on this, and we'll come back to the answer to this question. And after that, I'll do a few more questions, and that should conclude our lecture on section 2.2. All right, so I will be back I'll be back in a couple of seconds. I think you'll have to click on another video segment when you are ready for an answer to this question.